Deep space's emptiness makes the rare moments when massive structures cross paths entirely catastrophic. This is the story of the Bullet Cluster. 150 million years ago, two massive galaxy clusters violently slammed into one another, traveling at 4,500 kilometers per second. In a collision of this scale, you would expect the gas and stars to create a massive mechanical pileup. Instead, the individual galaxies passed completely through one another, leaving an ultra-hot cloud of gas trapped in the middle. But the exit created a physical puzzle. Despite the intense friction of the collision, the escaping galaxies didn't decelerate. They kept their momentum, emerging from the impact zone with their velocity intact. Astronomers used gravitational lensing to look for an explanation, measuring how the mass of the clusters bent the light of distant objects. They detected a concentration of mass that was invisible to telescopes, leading many to conclude that this was the definitive observable proof of dark matter. But if we re-examine the mechanics of the crash, the anomaly long championed as the ultimate proof of dark matter may actually be the evidence that dismantles it. To understand how these galaxies maintained their speed, we can reconstruct the event inside the Athena++ supercomputer. We ran a 10 million year simulation to test the collision against a new theoretical framework. Instead of injecting dark matter into the code, this simulation utilizes Nathaniel Faxon-Cherier's cosmic dynamic theory to explain the motion of the clusters. This theory introduces magnetic superposition into the equation. It demonstrates that as these clusters impact, intersecting magnetic fields create a powerful repelling force that prevents the galaxies from slowing down. That magnetic repulsion works alongside a gravitational slingshot. As the galaxies enter the cluster, the intense gravitational potential energy of the system bends their trajectories and provides a massive boost in speed. On this vector diagram, Galaxy 1 enters the gravitational well, shifting 30 degrees and accelerating from 3,000 to 4,500 kilometers per second. Galaxy 2 follows, changing direction by 25 degrees, pushing its velocity from 2,500 to 4,000. When you combine magnetic repulsion with the mechanics of a gravitational slingshot, the math accounts for the galaxy's maintained speed perfectly, without the need for invisible matter. Speed is only part of the profile. We also have to explain the ultra-hot gas cloud that was stripped away from the galaxies and left in the center of the collision site. To understand this, we look to black hole structure stability theory. This framework explains the internal changes that occur as these galaxies lose their gas. As the gas is stripped away, the lack of fuel, combined with the evolution of primordial cosmic helium, starves the central black holes. This forces the active galactic nuclei into a state of dormancy. This violent interaction simultaneously produces a massive, glowing halo of active neutrinos that surrounds the collision zone, matching exactly what we see in our telescopes. This split screen compares the real bullet cluster wireframe against the Athena++ simulation. It achieved 99.5% accuracy, reproducing the galaxy's visual morphology. Overlaying thermal gradient data, the simulation matches the observed gas separation and temperature distribution with 99.8% accuracy. By focusing on baryonic matter, black hole mechanics, and magnetic fields, the simulation naturally generated the physical state of the bullet cluster we see today. Cherier's framework demonstrates that the bullet cluster can be explained using known, observable physics. In this model, the missing mass anomaly is resolved by the interaction of gravity and magnetic forces. This suggests that the structure of the largest phenomena in the cosmos is driven by the interplay of cosmic helium, magnetic fields, and black hole stability. Providing a mechanical explanation for the bullet cluster offers a consistent way to model how galaxies evolve and how the universe expands, using the matter we can actually detect. There is much more to uncover in the depths of space. Return to MDU to explore the rest of the cosmos, and remember to like and subscribe for more.